Okay, so we have that the maxes and min, so we have the graph of f at x, and we want to graph the derivative. So the derivative is 0 at maxes and mins. So those fall to be x-intercepts. And then when the gradient is positive, that's above the line. So these all have gradient above the x-axis. So like here. And then when it's negative gradient, it's below the x-axis. So something like that. All right, figure 1's got functions. Figure 2 are the graphs of the functions, the derivatives of the functions, sorry. And we want to match. Okay, so you can kind of think about the overall picture. This is linear, so it's in this form. And the derivative of that is just m. It's just a constant. So that's going to match with C. This is a cubic or something like an odd degree. So that's going to be, the derivative is going to be a quadratic or some even degree. Okay, so that's that one. And notice it's all negative gradient. And that's why it's under the line. So F2 is E. This one is quartic, maybe, something like x to the fourth. So the derivative of that is going to be cubic. Oh, I messed up on that one. Okay, so this is B. This is not C because this is positive gradient. We need negative gradient here because this is down. This is negative gradient here. So this should be A. And this is quadratic. So derivative is 2x, which is a line, okay? All right, 6. The following diagram shows a graph of f. And consider the following diagrams. Complete the table noting for the first derivative and second derivative. Okay, so we have positive and negative in the middle. So this has to be the first derivative because it's positive and negative in the middle. And then if we want the derivative of that, this is negative and then positive. So it's not going to be this because it's quadratic, it's going to be linear. So we want negative, then positive. So it's negative until here. So not this one. That's negative until the origin. So it's got to be this one. Okay, the diagram below shows part of the graph of the derivative. Now we want to sketch the second derivative. So maxes and mins at Q become zeros. And then we have positive gradient. And then we have negative gradient. This is like x squared, so the derivative of that is going to be 2x. Not exactly x squared, but some version of it. Okay, so then write down the x coordinate of the local max point on F. So if this is the derivative in the top picture, this gradient, because it's the gradient, is going from negative gradient to positive gradient, okay? So this is the minimum. And then we still have positive gradient to negative gradient. So at R, x equals R is the local max because f at x changes from positive to negative at x equals R. Okay, write down the x coordinate of the point of inflection. Okay, so that is when the second derivative equals 0, or if you've got the first derivative, there's a max or a min. So that's happening at x equals q. So either because max on f at x or 0 on f prime. And second derivative changes sign. So remember, for it to be a point of inflection, it has to change sign. Okay, so number 8, g is a function from 1 to 7. G has an inflection point at P and a min at M. Partial sketches of G and G prime and G double prime. So use the information, so write down the x coordinate of P, which is the inflection point. So that's here. So for A, x equals 4, and justify your answer, 0 on second derivative, and changes sign. And G double prime changes sign. Okay, and then for B, write down the x coordinate of M, which is the minimum point. So remember, we have to look at the first derivative here. So we've got negative gradient to positive gradient. So that's happening at x equals 2 because first derivative changes from negative to positive. Given that g at 4 is 0, sketch the graph of G, mark the points P and M. Okay, so let me get rid of that. So we have, it starts G at 4 is 0. Okay, so we have, that is going to be the inflection point, right? And then if you think about this is linear, this is quadratic, we're gonna have a cubic. So it's negative gradient at first, and there's a minimum at x equals 2. So negative gradient, so we're gonna have like this, and then there's a minimum at 2, and then there's a point of inflection where it goes from concave up to concave down. All right, so then there's a maximum at 6, so something like this. So it's positive gradient from 2 to 6, and then it starts going down, something like that. It can be kind of any stretch, vertical stretch on that. All right, number 9. So the diagram shows y equals f of x. The tangent lines to this curve at A, B, and C are parallel to the x-axis. That means they're maxes and mins, or C is a stationary point. Okay, so we've got at A is a 0, at B is a 0, and at C is a 0, okay? And then we have positive gradient at till A, and then negative gradient till B, like that. And then after B, we have positive gradient until C, well, and then we still have positive gradient like that. Okay, so it does not go under the line at C. Okay, and then we basically treat this as our gradient function now, or sorry, our original function. So at 2, it's going to be, hold on. So that's a point of inflection a little bit before 2, so that's a 0 here. So concave up. So like here's another point of inflection. And this 4 is another point of inflection, stationary point, okay? So we have negative gradient. So I'm looking now at A and treating it like it's f at x. So we have negative gradient up until 2, so something like that. And then after 2, we have positive gradient to like here. Oops. Something like that. And then we have negative gradient until 4, and then we have positive. Something like that. All right, 10, the diagram shows the derivative. We want to go back up to the original function, okay? So if this is a cubic, we're looking for like an x to the 4th, okay? So this is the derivative, and here the gradient is negative, the derivative is negative, the slope is negative. So on the original function, it's going down, and then it becomes positive here. So that's going to be the minimum. Okay, so that's the minimum for f at x. And then, so it's going to be positive gradient here, and then it becomes negative. Okay, so this is going to be the maximum. And then it's negative there, and then it becomes positive again here. So that is another minimum. Okay, the point of inflection is where the derivative of the derivative is 0. So this is a point of inflection, and also it's changing sign. So it has positive gradient here and then negative gradient here. This is also a point of inflection here because it's got negative gradient on the left and positive gradient on the right. Okay, so now 11, diagram shows the graph of the derivative. We're the same as previous one. So we've got, so this is like x to the 4th, and we want to go back up to x to the 5th. So some even function, which is like a quadratic, maybe a little bumpier, and then some odd function like a cubic. Okay, so we have positive gradient, because this is the derivative. So positive gradient to negative gradient. So this is a maximum. And then we have negative gradient to positive gradient. And then it's something like this, okay? Because it still is positive, but yeah, this, well, I'll get to that in a second. Anyways, so if it goes here from negative gradient to positive gradient, this is going to be a minimum. And then that's all we have there. This is not a max or min, but a stationary point of inflection. All right. We also have, this is a point of inflection because it changes from positive to negative. And we have this is a point of inflection because it changes from negative to positive. All right, the diagram shows a sketch of the graph of y equals the derivative from a to b on the grid below, which has the same scale. Draw a sketch of the original function. Okay, so this is the derivative. We have positive gradient here. So, you know, something like this. Till here is a maximum, okay? And then we have negative gradient up until here, where it becomes positive after. And this is, yeah, that is a minimum. Now we have points of inflection here. So that's a point of inflection. And we have a point of inflection here, which is like there. And that's that, okay? Now 13, f is defined from -4 to 3. The graph has local max at 0, min -3 and 2. Write down the x-intercepts of the graph of the derivative function. So for A, we are going to have that the maxes and mins are going to be the intercept. So -3, oh, this is for the second derivative. Okay, so we're going to have x is -3, and then we're going to have x is 0. That's x-intercept on the first derivative, and we have x equals 2. So those are x-intercepts on the derivative function. Okay, so write down all values of x for which the derivative is positive. So that's when the gradient's positive. So that's from -3 to 0, and from 2 to 3, okay? Okay, so maybe we shouldn't include 3, whatever. Okay, so at point D on the graph of F, the x coordinate is -0.5, so like here. Explain why the second derivative is less than 0, because it's concave down, because fx is concave down at that point. Now sketch graph of the second derivative. Okay, so we need the points of inflection. So let's say, like here is going to be a point of inflection, and then like here at 1. So if you see, this is like concave up, this is concave down, and this is concave up. So we need concave up, concave down, and concave up.